start also with some definitions, but then I hopefully pretty soon get on to the tester's perspective. This is a link to a short movie, which I can highly recommend. It is the result of one of the EU FP7 projects already back then, so it has terminated, I think, 2-3 years ago. Back then they already tried to come up with a reference architecture for the Internet of Things, so that solutions become interoperable, that components become exchangeable. They have a pretty nice video which talks about that we even would need to think about how to interconnect plants or animals, because it's really getting an understanding of our physical world, and that includes not only the machines we build, it doesn't include only the people, but it might also mean that we know about an animal, where it was grown up, and so on and so forth. Okay. This, however, is already quite old for our fast-moving days. It shows that interconnected car could even be involved in an accident on the street, which I, from today's perspective, would say this is a wrong picture, because part of the IoT idea is to prevent such accidents. It's about making our lives more comfortable and more secure. Yeah? So it's really about improving things. And there are some numbers which I always find important to see if one, so to say, looks at the right things. There are different studies which talk about exponential growth for the interconnection of devices and systems. The mobile trend is still ongoing. Also, there is some saturation to be seen. And also, very importantly, the data streams which are exchanged via the internet are growing and growing and growing. So, in other words, on the one hand side, it's about the interconnection of everything. On the other hand side, it's about data. Data turns to become very central, so everything in the real world becomes a digital, or gets a digital image, and out of these images we try to find new insights, new understandings, new control mechanisms. So now two first definitions. One is from the IEEE, which gives a rather technical definition that IoT is a network that connects uniquely identifiable things to the internet. Information about the thing can be collected, and the state of the thing can be changed from anywhere, anytime, by anything. Well, for me, this is correct, but it's way too technical. It's just about the things. So it doesn't talk about the people. It doesn't talk about organizations, processes. It doesn't talk about, so to say, the intent, why we should interconnect the things. So ISO, I think, came up with a more succinct definition, because they bring forward the intelligent services that serve the people in order to process information of the physical and the virtual world, and to enable reactions on the insights we gain. Yeah, so there is the idea of a control loop. So first, monitor, understand, make some simulations or suggestions about possible futures, then decide and monitor again and see how their actions made a difference or not. Okay, we at the Institute in Fraunhofer focus, so we are in applied research. We drive quite some application domains. We come about the understanding that, well, many people just talk about IoT. I do think it needs a lot more differentiation, because the wearables that we used to have are rather on the consumer side. They differ a lot from the IoT solutions we seek in industry for automation, for interconnected production, and for interconnected products. Of course, that has a link to the consumer electronics. And again, it differs to the internet solutions we seek in public infrastructures. And I mean with differentiating that the contexts are different, the services which are needed are different. Yeah? And along that we need to see what are possible technical solutions at the end. But first, we need to understand the scenery and the context, and we think, well, this is a first rather important differentiation to know if I talk about the interconnection of an energy network or the interconnection of wearable to the smartphone, okay? And then there are a lot of cross-cutting concerns. One is how to identify things, processes, and people, and how to identify them securely. It's about the safety, so we are in a rather often in environments where the solutions supported by these interconnected things are in safety-critical environments. It's about security, and that I mean not only about the privacy, but also about being secure about on the information that is provided by these solutions. It is part of privacy to secure private data or commercial data, of course. It's about data, and then on top of that, metadata. So in the sense that it's good to know, well, for example, the temperature in this room, but one should also know from which sensor it's taken, how actual it is, how precise it is, for which reason that temperature has been taken. So it's about the data and the quality and the intent and the owner and the provider of this data, which all gets to the level, which allows us to meaningfully use the data. At the end, we are asked to build trustworthy solutions, as all these things are more or less critical infrastructures. I mean, the variable that doesn't count correctly the steps over the day, non-critical. Yeah? But the sensors which count the flying height of an airplane, very critical, okay? And again, depending on the context, we need to see how to make them strong enough and how to make them such that they can be efficiently composed from different components and solutions all over. And well, we had already this morning a lot of discussion about the different definitions. I only showed you two. I now show you a couple of other links to definitions and to reference models even. So IoT is a driving idea through many different areas. So ISO, IEC, well, comes more from the technical side, IEEE from the internet side, and IETF, the IIC, Industrial Internet Consortium, that started to combine the industrial perspective with the internet perspective. We do have the ITU that more naturally comes from telecommunication, mobile communication, and so on and so forth. I don't need to sort of say go through all the different initiatives, but they all have some specialities in their view on an IoT solution. At the end, the World Wide Web Consortium, which sort of say thinks about the web as a web of things nowadays. Okay. To sort of say bring it together, we started to lay down some principle. I even only call it communication architecture, because that is a very limiting view on what are the principal components in an IoT solution. And I think here this is rather important to understand. There are different initiatives which drive towards interconnecting things and processes and people. So one is from the industry, the OPC-UA, which more or less becomes the de facto standard for Industry 4.0. We do have the MQTT and the, well, that I'd say is more the internet connection. Then the OMA is from the OASIS side, and we have the lightweight M2M, which is from the telecommunication area. Yeah, and well, I'm not having seen quite some approaches to find unified things, unified platforms, unified programming languages, unified modeling languages. I don't believe in this. I believe that every technology has, say, certain advantages and disadvantages as always, but they are typically built for a purpose. And a telecommunication purpose is different to an automation purpose. So that I believe that we will have a plethora of technologies underneath, and then it sort of say needs to be efficiently integrated and sort of say also computed. Well, first computation to take place near the place of sensing, because the solutions need to be resource efficient. We need to take care that not too many, well, airspace, so to say, is used for data transmission. So we do have, after the node connectivity, the edge computing, so that condensed set of information is only put forward to the cloud or to clouds of clouds, interclouds, hyperclouds, whatever, so that here we make or store and further process only the initially pre-filtered data, and then we come to the services, processes, endpoints, and applications on the devices with the users. Okay, I'd say this network level. This is the pretty, well, this is active research and engineering, because also we are in networking now for, well, 50 years already. Those interconnections of devices and systems impose new requirements, that here it's really about how to very efficiently and in a secure manner communicate data upward. Then the platform level, I'd say, well, this is a kind of already established along cloud computing. And then on top, we also pretty well know how to develop multi-OS, multi-device, multi-technology applications so that they can be used along different devices. Okay. This is just where the technology comes from, we think. Then another very important view is from the architectural perspective. I just put forward here the more SCADA view on critical infrastructure, which is very solid and so to say well-defined, what is done on which level, and very static. In the IoT, we think that we really talk about a very open, dynamic, scalable set of services which are orchestrated. Yeah, and they can be on different levels of this communication architecture I've shown you before. So that means we need to, so to say, also turn our methods from a more static view to a very dynamic, open view, which, so to say, implies new requirements, how to secure them and make them stable, right? So they could be just unstable by terminating components, not accessible components, whatever. Okay, good. And then, of course, well, people looked into that area already for quite some time. In research, I'd say Internet of Things has been coined to be cyber-physical systems. Their quality, again, is critical, which is also supported by a more recent survey we had. on the, well, sorry for this German. So it is a survey with C-level executives in German companies, and they really put high emphasis on the quality of their systems. Okay, that figure I had before this morning, so which is a kind of principal view on how we should develop systems in a model-driven engineering kind of way, where we sort of say turn the initial requirements into system requirements, system model system, and then do a comparable parse down to the test system, so that we really have a separation of concern for both sides. However, in the Internet of Things, the system under test itself becomes a rather complex, heterogeneous set of, or system of systems, where we sort of say have to come up with different means to test the system. It's not just one test system, but it's rather a combination of the test components, simulated functionality around the system, then real devices and real test devices, and also supplemented by monitoring support in order to know various aspects. So the testers drive kind of the top-level interfaces, and miscellaneous interfaces are analyzed with support of the monitors. So now getting back, so what does this all mean for the testers? Yeah. So first of all, I think, well, we don't talk about software testing, but about protocol testing. And who has ever been in telecommunication, this is a sort of say a kind of separate field still. In testing, this is specifically about conformance and interoperability, and also about performance testing. So how scalable is a base station for foreseen a set of mobile users, for example? Okay, but I'd say a kind of, we know what needs to be done. Of course, the protocols on the left-hand side, they are kind of new. They are extensions of existing protocols or specializations of existing protocols, but it's clear how to test them for conformance, interoperability, performance. Well, then we have the application level. Well, I often stick to the Eclipse environment because it's rather open, and many researchers and companies contribute to that. There's a strong IoT project already going on. For example, Bosch is submitting their, and they have quite a lot of interesting plugins ready to go, implementations of the protocols and support to build applications on top. But there are many others. So, however, we from the, again, engineering side should look for open interfaces so that the developments can also be reused by others. So this application level, platform level, this is rather standard, I'd say, component testing, integration testing, system level testing. There all the software testing methods apply. Now, well, anything new, of course. So I said new challenges. It also comes with new challenges to the testing. I think most of all, it's about security. Yeah, and security so far, we do have a rather static process along CROM criteria by ISO, where where the testers or certifiers take a snapshot of a software or a product and then assess it to be secure. But this is without consideration of the system in operation, in the, so to say, using processes. There is
there are by Mitra and others a lot of lists about software weaknesses, vulnerabilities. There are security patterns, there are security test patterns, which sort of say need to take into account. Here I really believe that we still are too much in the lab environment. However, IT security is a lot about software in operation. So if you have, well, my husband is in safes, money safes, and it's always funny to hear if he can open the safe because the standard password is still in. Yeah, you can make it as secure as you like, as long as you sort of say, leave the default settings. Nothing is secure anymore, right? And that I think you know also from your software systems. They need to be hardened, we say, right? They need to be made secure in operation. And as long as the security certificate only consider the pure software, they do not consider the software system in operation. So, and then of course it's about, well, all the complexity around. So it starts again from the intent, what the system should do that relates to risk. That risk should drive the testing efforts and the test design. We call it risk-oriented testing. Then there's fast testing, which is about randomizing the functional testing at the edges of the functional correctness, because an almost, well, incorrect inputs to a system are typically rejected, but only slightly incorrect inputs or almost correct inputs aren't. And there is typically the vulnerability in a software, and that fast testing tries to get to. Yeah? And online testing is this idea to turn testing into the target environment, which is of course dangerous because you are in a productive system, and then you need to be very careful what to do when with the running system. And last but not least, as I said, well, IoT, well, is first of all about connectivity protocols, but then it's about the data that is being processed and out of which we want to gain new insights. So, and if the quality of the data is bad, of course, you can derive anything, but this is, well, most often useless, and it might be dangerous. So, well, there is a big question on data quality. There's quite some research by the database people. I think this is way not enough because, well, also they just basically approach it via structural considerations, but not yet via semantic considerations. So, but, well, I do not have yet myself a good direction where to look at. We did quite some on metadata quality. That was a kind of easy, I think, because there the purpose is clearer. With the real data, it's about the good reflection of the physical world, and that is even a philosophical problem. So what is a good digital picture? Well, this is already down there quite interesting, right? So security testing, online testing, data quality. But this is not all. We do see that quite a number of IoT solutions run in harsh and unreliable environments. So far we develop software for computers which are used in-house. So they are in a, sort of say, rather calm environment, it's sort of say in normal range of physical conditions. But as soon as you want to use intelligent streetlights, the computers get into environments which are a lot more wet, and they need to sort of say work over a larger range of temperature, of course. Yeah? So we need to add simulators for the environmental conditions as we do for power control software in a car. Those software environments use those simulation environment as well. Then I showed you this view on orchestrating services and components. So the systems themselves are highly dynamic, and they use quite heterogeneous sets of devices which come with a heterogeneous set of interfaces. So that means we need to develop an understanding of what are good reference configurations which we use to evaluate the systems, and how do we adjust and scale test configurations dynamically. So forget about static settings. Even as of today, you could say, well, 80% are still static. I think this will turn in quite some years, and we need to prepare the test methods to be ready for very dynamic environments. And then this is all typical. Well, every technical system has resource constraints. So the systems are strong enough to just put any test software in addition to it. There are, so to say, the very small devices up to the large devices, but they are, first of all, real-time devices. So a test system itself needs to become real-time as well. So it needs to be at least as fast, I say, as the system under test. And that again depends on the target test system, on the target system under test. Yeah? And then it's again a combination of discrete functionality and continuous stream processing. Yeah, if you sort of say take again the power control in a car, it's for the driving dynamics. This is just streams of sort of say the physics in driving the car. Okay, now what could be a test platform for the Internet of Things? I do believe then extracting all the concepts you're going to need, we can extract also the test concepts needed. And we started with such a platform years ago. That is this TTCN3, Testing and Test Control Notation, which has its natural roots in protocol testing, which was extended to software testing as well. And later on, we extended it to add real-time features in order to address embedded systems. And we have, for example, TTCN3 engines on real-time operating systems. Yeah, so that you really can address, depending on the system under test, the correct, or can choose the correct test system implementation. But I think in order to manage those dynamic configurations with real and virtual devices on the system and the test side, well, I call it for a moment TTCN3 virtualized, which is kind of able to better master and manage those configurations which need to be come up with. Okay, good. That now a kind of sums up my view on the tester's perspective. So the baseline is test automation. So I think the discussions are over if manual testing would be appropriate. I say clearly no. When doing IoT testing, it should be done with test automation. And that test automation takes bits from protocol testing, software testing, system testing, and security testing. I, for example, do not place here safety testing because safety is realized via functionality and security. So the test methods are in these 4 areas, at least to my best knowledge and understanding. Okay. I have a couple of minutes left, so let's look a little into TTCN3. I only give you a rough idea. So that is a test technology which allows you to specify tests rather precisely, and then by use of tools and execution environments, you can automatically run them. So, and it's a language, first of all, which is rather easy to comprehend for testers. So it talks, for example, about a test case which sends something and then is ready to await a couple of responses or missing responses. And depending on the match to the expected response, it says pass or fail or inconclusive. Okay, so this is one test technology for different tests. I don't say for all tests because I do think it needs to further evolve along the upcoming requirements, but it supports distributed testing. So a TTCN3 test suite can run on one computer or on a network of computers which are used as test devices. So it has graphics integrated for better documentation, but it has, most importantly, an open test execution environment. And test device vendors took it up and now support their execution environment, or the execution interfaces of TTCN3, so that TTCN3 test suites can be executed on those test devices. The test cases are not static. They adapt during test execution. They adapt in several ways. So one is this ability to accept various responses from a system. The other one is to construct the objects or messages sent to a system depending on the results received before. The other is to create a test component or terminate a test component, to establish links to the system under test, to create another system component, whatever. So this is really a full dynamic programming environment, plus a means to assess the interaction between test system or network of test systems and network of systems under test. So, and along that, you can then have active test components or passive. You can add impairment generators, monitors, whatever needed. Okay, and the language is also parameterized throughout, so that even at runtime, I can say this time I want to run 1,000. Next time I want to run 100,000 test component with a different percentage of functional scenarios that they run, for example. Okay, so it started naturally with regression testing for test automation and conformance and interoperability testing, and later on was extended to real-time performance, load and stress testing, as well as security testing. And if I write this, I mean there are concepts implemented in the language so that such a security test suite is naturally supported. Yeah, you just say where to fuzz, for example, a certain data. So it's a language. So you have a test specification. This goes onto a test device which interconnects to a system under test, and then via message exchange or object invocation, test system and system under test interact, and so to say it goes back and forth, and along this evaluation the tester says yes or no to a certain system behavior. And in order to make that working, there's the idea of an execution engine which is surrounded by a couple of open interfaces, which, for example, are used for test management. So we have that interface. You select the test suite, you select the test suite, you test cases, you configure them, you parameterize them. There is an interface to logging, which is underneath an XML-based format, so that whichever documentation of the test execution you want to receive can be, so to say, defined along that. There's an encoder-decoder interface. This is pretty much from networking because, so to say, logical data is transmitted in some bit format. And then there's component handling in order to cope with a network of test devices where test components can run here or there. Okay. And then there's a real interface to the system under test. Could be a couple of system under test interfaces for the interaction. And there's also a platform adapter because you do not only have the system under test device, but also test system devices. And that could be real devices or simulation devices, for example. And there the timing is different. One is a wall clock time, one is a simulation time, and that is done all in the platform adapter, which also is the backdoor to add functionality which you don't want to put into the test specification. Okay. Good. And now, so that has been, well, I think the first version was published 2000, and since then it further evolved. But with the testing of embedded systems, we added, for example, the concept of signals, of timing, of control flows in hybrid systems. We added the support for sampling in such a test system. So this is in embedded systems, they are clocked, so there are sampling rates or cycles of behavior which need to be addressed. There is the need to simulate the physical environment and to evaluate continuous signals and to produce continuous signals. And of course, you need to coordinate the schedules of the distributed test components. That is, so to say, the engineering part. The conceptual part, we added an understanding of hybrid automata into TTCN3, where, so to say, from state to state, which follow a certain, set of differential equations, you have triggers to, so to say, come from one behavior to the other, and that you can, so to say, then specify comprehensively. And then it all, again, gets into a rather readable specification. I think this is, not yet as easy as before, but once one understood how those embedded systems work, the hybrid automata are kind of clear. So we continuously provide some data and then await the triggers to move on, for example. And that all can go into a MATLAB Simulink environment. For example, to evaluate car-to-car communication, where we do have a test stand with onboard units and head units and navigation systems of 4 cars. Then we do have the test data that we either specify or take from traced car movements, so that we, turn the real data into test data, and we run the test suites and receive the functional test logs and also the logs on the navigation systems to see if, the logic follows the functional message exchange in the car control. Okay. And then, you can run those things for up to 4 cars, and then come for example, with test suites, which evaluated in Germany the onboard units by Audi, Bosch, and so on, if they work as expected and if they, work also in an interoperable manner, because for car-to-car, in order to work, it shouldn't matter if there's a BMW in front of your BMW or not. Okay. Good. Time is running. Short snippet on another extension we did is for security testing, where we run European project Diamonds, which combine test automation with functional testing for the countermeasures, risk analysis in order to know what to test, and then adding this fast testing in order to randomize the testing to see if there are unexpected vulnerabilities in the systems. And we did this for quite some application domains. For example, in Germany, we evaluated banknote processing machines. They are, well, really for the national banks where they do count the US dollars or the euros or whatever. And they opened those machines for remote control and maintenance. And that is, so to say, a potential entry point to tweak the computation or the counting of the banknotes. And at the moment where the banknote think it's only 1 million euro, but not 2 million euros. So this is a starting of, so to say, for a theft to take the 1 million. Of course, this is all in very secure places, and there's all physical security measures, but they were still really afraid of having a logical vulnerability so that someone could attack the system. Yeah. And what we did, we used this CARAS, model-driven risk analysis approach, which we further extended from Norway. Then this turns, well, to make the story simple, into sequence diagrams, which we then fuzz, so randomize. So out of 100 test cases, you create 10,000 and more, which we sort of say translate to TTCN3 and then run automatically via the application of the banknote processing machines. Okay, and well, it's under NDA. What so to say we realized with this testing approach, but more or less those banknote machines have evolved over years. They are rather matured. So and there were easy fixes for the things we detected. So there are a couple of experience sheets from the different domains on product cards, automotive, smart cards, banking, industrial automation, and telecommunication. And there are also evaluations of the process which we developed in order to improve testing in those companies. And we used the spider diagram to show where it improved the most. And, well, yeah, I leave it like that. So this one I also showed already. So I do believe that it's nice to develop standards, tools, and even spin-off companies that we do, but we should also train people in order to make use of those new concepts and technologies. So I can really repeat that the ISTQB curricula is a good thing to do, and we hope to extend it even further also along the things that happen around IoT, and we'll see where we place the modules for that, because it is a kind of new species of technical systems, at least from the software testing community. And so for the embedded system testers, like the protocol testers, like the software testers, are rather in separated communities, but they all need to come together because we develop solutions which need to work to the top processes and dashboards and cockpits which are being used at the end. Good. This work has been started, well, from Germany, and with a rather easy jump start, we had DB Systel, SAP, Atos, and, well, rather small and medium-sized enterprises in the Testing for You initiative. And we will sort of say not only address it from the testing perspective, but also from the constructive quality assurance perspective, because testing assesses quality level, but foremost it's about how to construct those IoT solutions correctly in first place. So this time we want to really take both sides, so how to construct them efficiently and in a trustworthy manner, and then how to assess that they do what they should do. And well, we hope to have first results next year and to pilot it in Germany and then to see how to make it well available to the international community. Okay, to sum up, I love to repeat this Andresen statement that software is eating the world. Maybe that is not new to you, but it's a really nice sentence. So at the end, it's all about software, and our societies have learned to cope with technical systems which are more hardware related, and software adds new dimensions, and software engineers really is a new expertise which we need to support. The Internet of Things creates new critical infrastructures. Nowadays, well, 10 years ago, energy provisioning was the most critical infrastructure we have in our urban environments. Nowadays, ICT infrastructures, so telecommunication networks, are likewise critical. There is no energy network without telecommunication, and the other way around. Yeah? And by that, so to say, we need to ensure that it's working. So 2 days outage in a highly urban space is already catastrophic to the people. Just think about emergency services which won't work anymore. By that, it's about security, safety, privacy, trustworthiness. So functionality is, of course, the key, but security, privacy, performance, safety are likewise key to those software-based systems. It's not only about quality assurance of software, but we need to take the systems perspective, which means protocols, services, data, and systems of systems. Well, and then, as I said before, we need to find new ways how to extend lab testing into online testing in the production environment, to find efficient ways for safeguarding. And well, online certification is just an instrument, but at the end it's about the online safeguarding of the system. And then, of course, call it smart grid, smart city, industry 4.0, open government. One has a different perspective on a rather common set of challenges and risk-related aspects, which we, so to say, from the quality assurance perspective, need to support in a constructive way and analytical way. Okay, thank you very much, and maybe we have time for questions. Yeah. Well, if not, then thank you. Okay, yes, please.
You mentioned about automation.
Yes.
And that IoT should require
Test automation.
If it is with modeling, do I need a variety of, I'll call it modeling views to model things like the real world and security and these other things you mentioned? So it isn't a single model.
No.
It's a bunch of models.
It is. Yeah, I think definitely it's a bunch of models. It's a set of models on different levels of abstraction and from different perspectives and by different stakeholders, because also modeling is done with an intent, with a purpose, and so to say, depending on who is modeling something for doing something, the model will differ. And then it's about consistency or compatibility between this network of models, I would even say. So we will see the other way around. Nowadays, we rather see centralized approaches to model-driven engineering. It's top-down. It's basically used in development. There are already quite some interesting research results how to use models at runtime, but it's still, so to say, a system view with a single-entry system model view. Of course, underneath there could be several more models, but I think for one system, it starts to have, we start to see different models by different stakeholders. It's a little along the line of ODP, Open Distributed Processing, which already came across the idea of viewpoints on the system. I think those repeat on the modeling level, and also you could say MDA also supports this line of thinking, that there are, so to say, the business models, the technology independent models, the technology dependent models, and so on and so forth. So no, definitely that is also research to be done and engineering at the end. Well, we do have a first paper on the Internet of Systems Engineering, we call it, where we sort of say support cooperative development and quality assurance by use of modeled software and devices. Thank you very much.